All right, so we're going to finish up chapter 3, which is on looking at systems. All right, it's really a review of just graphing and finding an intersection. And then we'll look at section 4.1. So just a reminder of what a system is. Okay, a system is when you are solving for 2 or more variables, and I give you 2 or more equations. Now, most of the systems that we've solved, if we've had any, have been linear. We're going to look at some that are nonlinear. When you graph, if you're trying to solve a system, what are you looking for on the calculator? Yeah?
An intersection.
Right. You're going to be looking for an intersection point. Because you're looking for a point, you need to tell me an x and a y value when you solve a system. Or you need to tell me 2 variables. You can write those variables as an ordered pair, or you could do x equals y equals on separate lines. You could do that. But you do have to tell me 2 numbers. So as I just asked, when you're solving a system graphically, you're looking for the intersection points. The biggest thing that goes wrong here is people do not look off the screen. Okay, we know, or we have an idea of what polynomials look like. So you need to keep that in mind and think there could be something off the screen that you have to look for. Right? Because if it's there and you don't look for it and you miss it, then you'll get it wrong. Okay, so they want us to solve this graphically, but what letter do we need by itself? Because we can't put that in the calculator like that. Yep. Y. What would be your 2 steps to get y by itself in the top equation?
Subtract 2x from both sides, and then divide both sides by 3.
Okay, so subtract the 2x. So it's going to become a -2, and then divide by 3. So our slope is -2/3 x, and we have 5, and we have to divide by 3. Okay, how about for the bottom one? What are my 2 steps to get y by itself there? Yeah?
Add 3x to both sides, and then divide both sides by 5.
Add 3 and divide by 5. So +3 divide by 5. That's your slope. And then you're going to have the 21 divide by 5. Okay, those are both polynomials. What kind of polynomial is the top one and the bottom one? Yeah?
Linear.
Linear. And they're not parallel because the slopes are different. So how many times can linear polynomials cross if they have different slopes? 1. If they have the same slope, there's a couple cases, but these are different slopes. Okay, so let's put them in. -2/3 x plus 5/3. There's other ways to type that. That's how I do it. Okay. And 3/5 times x plus 21/5. Okay, so make sure we got everything typed in right. Looks good. Do zoom 6. Here's my first line. Here's my second. And what are we looking for again?
Where it intersects.
Where they intersect. So second calc intersect. So you could write your answer like that, or you could write your answer as a quarter, -2, 3. Any questions on that one? Okay. So that's linear. Now, let's think about these 2 polynomials. How many times can the top polynomial turn at most? Yeah?
3.
It can cross the axis 3 times, but 2 can turn twice. How many times can the bottom polynomial turn? Yeah? Once. So think about the most complicated situation with a cubic and a quadratic. I think that would be as many crossings as you could get. I don't think there's any other way you can arrange those to get more. And three would be the most. Okay, and I know that these could never cross again out here because a cubic is always going to beat a quadratic, right, in terms of the steepness. So the cubic is going to stay on the inside, and the quadratic, it's not as steep, it's going to stay outside. So there's no way they can cross again over there. These two are going in different directions, so there's no question that they never cross. So I think that's all we got. Okay, so let's graph it and determine the number of solutions. Okay, they're not asking for the solutions, just how many. 3x squared plus negative 2x plus 5. Okay, do zoom 6. There's my cubic. Here's my quadratic. It's going to be concave down or flipped over because we got this negative in front of the 2, which causes it to open down. So how many solutions do we have in this case? Yeah, yeah, we do have 3. Okay, when you look at this, you got to realize that a cubic, again, cubic is always going to beat the quadratic, right? Cubic is going to have a steeper slope, bigger negative number than the quadratic. So eventually, these cubic and quadratic are going to cross. If you want to see it a little clearer, you could set your y-min at negative 45, and I bet that'll show it perfect. Yeah. But now you can tell the cubic is dropping off steeper. Okay, so yes, there are 3 solutions. So if you said 2, you're only looking at the 2 you could see in the standard window. You got to get zoomed down a little bit to see the 3rd. And last question for 3.7, they're throwing in algebraic and graphic in this one. Let's do it algebraically first. What method for solving a system is this pretty much already set up for? They're kind of handing it to you to use a certain method. Substitution. Yeah, they already got a variable by itself, so you just want to take what y equals and substitute it into the other equation. Okay. What would be our first step if we were trying to solve that for x? Well, when we're solving generally quadratics or higher, we do want to get something on one side first and then go from there. Yeah?
Get the highest degree variable by itself?
No, not the highest degree variable by itself. What do we always get by itself? Think about when you're solving a quadratic. It's going to be the same thing to solve this cubic. Yeah?
You're going to subtract 3x from both sides,
Right.
right?
You got to get it equal to 0 and then find the roots. Okay, that's what all chapter 3 was about, finding roots. Okay, so we move the 3x to the other side. Now, what would be my next step on the right-hand side? Yeah.
We should factor
What would you factor out?
x.
Yeah, factor out an x. Okay, so we factor the x out. What would we do now? Yeah.
Take the x squared minus 4, make it into x plus 2 and x minus 2.
Yeah, so factor your difference of 2 squares. And now, we should be able to find the 3 answers you could plug in. That would give you 0. What are the 3 values of x that give me 0? Nick?
0, negative 2, and 2.
Yep, 0, negative 2, and 2. Perfect. So algebraically, that's actually not a hard cubic to solve. It all factored. No synthetic division, no rational root theorem needed. If you wanted to do it graphically, there's two ways. You can either, once you get it equal to 0, graph that and see where it crosses the x-axis, or graph 1 and y1, 1 and y2, and see where they cross. I'd rather just graph one thing. So I'm going to graph this and see where it crosses the x-axis, because that's where the zeros are. So x cubed minus 4x. And we already know it's 0, 2, and negative 2. I'm just confirming it. Oh, perfect. 0, 2, negative 2. So that's looking at it graphically and algebraically. This second one, that might be kind of hard to do algebraically. It is set up for substitution. But you would have to get some nice answers. Because if you're going to be left with a cubic, somehow you got to get that down to a quadratic. And that's only going to happen if you can find a nice answer to divide through by and then turn it into a quadratic. So maybe that's why they didn't have us solve it, because maybe that doesn't happen. I don't know. Okay. Any question on that one? Okay, so that's it for 3.7. So now we'll spend the rest of the time on 4.1. So in 4.1, we still need to know all the stuff we did in chapter 3. It builds on that. So we're going to be looking at rational functions. Rational functions are functions that are fractions, where the top and the bottom are polynomials. When we were dealing with just polynomials, what was the domain for polynomials? Yep. It was all reals. Now we're dealing with a polynomial in the top and a polynomial in the bottom. Separately, the polynomials have domains of all reals, but when you put them together as a fraction, what do we have to make sure we don't do? Yeah?
X can't equal 0.
Or well, it is possible x
the
can be
whole
0.
thing can't become 0.
Right, the denominator can't be 0. Whatever value of x would cause that to happen. Okay, we don't want the denominator to ever be 0. That's what this says right here. So here's an example of a rational function. It's a quadratic in the top and a linear polynomial in the bottom. We'll talk about the domain in a little bit. Here's another one. It's a quadratic in the top and a quadratic in the bottom. Now, we spent all of chapter 3 looking at how do you find roots of polynomials. That's exactly what you'd have to do in g of x. You would need to find the roots of the denominator, the values that would make the denominator 0, and then tell me, don't use those numbers in the domain, because we don't want to divide by 0. Okay, so we're gonna try finding the domain of maybe those exact problems, f of x and g of x. I know we do f of x. That's f of x, x squared plus 1. Yeah. The other thing that can give you a problem is square roots of negatives, but you're not going to have square roots of negatives here. In a rational function, the top and the bottom have to be polynomials. To be a polynomial, you can't have a square root of a variable in there. So you won't have to worry really about imaginaries messing up the domain, just dividing by 0. Okay, so let's find the domain of this one. What is the domain of example 1a? Yeah.
All real numbers
all real numbers except for 3. If I asked you for a sentence, I would definitely accept that. That's perfect. All real numbers except 3. If I asked you to write your answer in set notation, you would have to write something like this. You could pick anything that's lower than 3. You could pick anything that's higher than 3. You just can't pick 3. Okay, so that's set notation. All right, this one, a little bit harder. We still have to figure out the domain. Okay, what would make the denominator 0? But what would make the denominator easier to think about if it was what?
If it's factored.
Right, if it was factored. If it's not factorable, we're going to have to use quadratic formula just to find the roots. That could take a little while. But hopefully it's factorable. Does anybody see how that factors? Yeah.
X plus 2, x minus 1.
X plus 2, x minus 1. Let's check it. X squared minus x plus 2. Minus 1 plus 2 is plus 1. Perfect. Okay. You don't have to worry about the numerator. For this, that doesn't matter. So what's the domain for example B? Yeah?
All reals except -2 and 1.
All reals except -2 and 1. So let's visualize that. All reals except -2 and +1. When you write that in set notation, how many separate intervals are you going to have to write? Yeah? You're going to need 3. You can pick anything lower than -2. That's the interval all the way unbounded on the left. Or we have the bounded interval between -2 and 1. Or we have the unbounded interval on the right, from 1 to infinity. So that's a pretty typical pattern if you need to exclude 2 values in the domain. And the top one I did, that's a pattern if you need to exclude 1 value. We're not going to get into ones where you have to exclude like 5 or 6 numbers, because then the intervals start to grow and get kind of complex. But 2 is definitely something you could see. Okay, and how about this one? Actually, that one's a little easier than the last one. What's the domain of this one? Yeah?
All reals except 2 and -4.
All reals except 2 and -4. Could you write that in the set notation for me?
Yeah.
So 2 and -4. Okay.
Negative infinity. 2.
Because you just included -4 in the domain. If you include everything between -infinity and +2.
Oh, so -4.
-4. Yep. Or
And then 2.
so the next interval always has to start with the last one left off. So those 2 numbers will always match each other.
Oh, -4.
Yep, -4. Up to
2.
2. Okay, so there's your bounded, that's the middle interval. And what's the unbounded interval that would be on the right?
2 and
2 to infinity. So when you write your numbers, they also should end up being in numerical order. -4, 2, and then 2. That's in order lowest to highest. if you start with negative infinity, okay, and do it like that. Okay, so there's a couple examples of finding domain of a rational function. So those rational functions we looked at, they're pretty complicated. They're not the simplest one. This is the simplest one. Okay? 1 over x. The top is a constant polynomial. The bottom is a linear. When you graph it, that one is going to look kind of like this. The calculator is not actually drawing that perfectly. The two branches of this graph look like they have starting and stopping, or at least starting points, or however you want to look at it. They don't. They go on forever. So if I draw that one a little bit more accurately, the curve should go on forever. But they never touch any of the axes. Never touches any of the axes. That's not true for every rational function, but it is true for this one. So looking at the graph, as x approaches infinity, which means as you go to the right, or as x approaches negative infinity, as you go to the left, what is the y value approaching? Y value approaches something but never reaches this. Yep.
0.
Right. It approaches, but it never reaches 0. Think about what happens if you plug in a number in that box, right, for x, a big number. Right? Plug in 1,000. If you take 1 and divide by 1,000, that's 0.001. Is it 0? No. Is it close to 0? Yeah, it's pretty close. It's 1/1000th. But this fraction, no matter how big of a number you fill in right here, will never be 0. It can't. What's the only way that a fraction can be 0? Yeah?
If the numerator is 0.
If the numerator is 0, and the numerator here is a constant, and it's never 0. The numerator is always a 1. So you can divide 1 by as big of a number as you want, and it'll get smaller and smaller and smaller, but it never reaches 0. Okay. So on the right side, your graph is curving down towards 0, and as you go on the left side, it's curving up towards 0. Okay. But it never will reach 0. When you have a graph that never reaches a certain value, but it just keeps getting closer and closer to it, that value that it gets closer to is called an asymptote. And in this graph, y equals 0 is a horizontal asymptote. It's a dotted line that we could put in that the graph never touches. When you write the equation of a horizontal asymptote, you do have to write it as an equation. Y equals. If you put x equals, and I'm asking for horizontal, that's wrong. X equals would be for vertical, which we'll do in a minute. So to figure out what your horizontal asymptote is, don't look at what's happening here. Who cares if it crosses the asymptote when x is like 5? We're looking at what happens when x is like 200 million. Okay, look at what happens when x is way on the right. Are you getting closer to something but never reaching it? If so, you have an asymptote. Now, some people think, well, with an asymptote, you never cross it. Okay, here's an example where that's not true. Here's another example. Let's say that line was an asymptote, and I had a graph that did this. That blue line is an asymptote. Or that blue dotted line. I'm crossing it infinitely many times. But as I continue to travel to the right, I am getting closer and closer and closer and closer to a value I just never stay at that value. But I am getting closer to it. So this is still an asymptote. The one in the lower left is an example of an asymptote, and you actually do never cross it. Right? You just get closer and closer and closer. But the other two you do cross. Any questions on that? Yeah?
I was just wondering if you were going to be doing the squeeze theorem.
The squeeze theorem? No, not particularly in this, no. But we could talk about it after if you want, because you're doing that other class, right? Yeah. Okay. Any other questions on that? All right, so let's try finding the horizontal asymptote and without graphing. So numerically, what you need to think of in your head is look at the part of the problem that has a variable in it. Just focus on that for a minute. I want you to replace that x with infinity. And I want you to tell me what's going to happen to what's inside the purple box. So what happens here if you replace x with infinity? What's going to happen to that fraction inside the box? Yeah,
Really small.
it's going to be really small. How small is it going to get?
I think it's really close to 0.
Yeah, it's going to get as close to 0 as you can possibly imagine. As x gets bigger and bigger, whether it's a really big positive value or a really big negative value, this fraction is going to get extremely small and very close to 0. If you take something that's as close to 0 as possible and add 2 to it, you're going to get something that's very close to what? Yep. 2, very close to 2. So 2 is the value that you get close to as x approaches infinity, but you never reach it. You'll get very close, but you won't reach 2. How would you write the equation of the asymptote? Don't just put 2. That's not an equation. Yeah.
I was just going to 2.
What is? Yeah, we got to write an equation. Yeah.
Y equals 2.
It's got to be a y, and it has to be equals 2. Okay. How about this one? Again, look at what happens as you let x be a really, really big number. Look at what happens to the fraction, and then minus 3 from that. And that's the number you're going to get close to, but never reach. So what's the horizontal asymptote in example B? Yeah?
-3.
Yep, how would you write it as an equation?
I don't know.
Yeah. Y equals -3. Okay, so on the test, if you have a choice, like a multiple choice, and it says y equals -3, x equals -3, and you pick x equals, that's not right for a horizontal. That would be for a vertical. All right, so I'm not going to get into the example. I just want you to be aware of it. You can have more than one horizontal asymptote. Here's a graph that has more than one horizontal asymptote. As you head to the left and you head to the right forever, this graph is tracked between two asymptotes. And oops. Why can't I get out of that? There we go. Okay. So just to show you, I'll go further to the left. I'll go like -20. 20. It's definitely trapped between two horizontal asymptotes. So we're, again, not going to get into that specifics any more than that. I just want you to know that that can happen. So this has a certain asymptote as you head to the right, and it has a different one as you head to the left. But it has two. All right, now I want to look at what happens to x if we pretend that it's a different value. I don't want to pretend that this is getting really big anymore. Okay, we pretended that it was going to infinity or negative infinity. What number would you fill in for x that would cause you to divide by 0 in this case? Yep.
0.
0. Now I want to look at what happens as we approach 0. So what's a value that's extremely close to 0, but not 0? Yeah.
0.0001.
All right, so 0.0001. Right, however many zeros you want to put in. If we take 1 and divide by 0.0001, what would that come out to? That's 1 divided by 1/10,000th. Yep, that's 10,000, really big number. So as this gets smaller and smaller and smaller, the entire fraction is getting what? Bigger. It's getting really big. And in fact, the smaller you make x, the bigger you make the entire fraction. How big do you think the fraction is going to get? Let's say if x gets as close to 0 as possible, what would your y value get close to? Infinity. Yep. So what's happening here is as you approach 0, plus means from the positive side. The positive side is always on the right. So if I put that graph back in. As you will start to approach 0 from this side, from the right side, all of a sudden the y value takes off and goes up to infinity. What happens as you approach 0 from the left side? This is the left side over here. What happens as I start to get close to 0 on that side? Davis? What happens on that side?
It just gets like super close to negative infinity.
Right. It's dropping off to negative infinity. If you want to see that, pick a really small negative number for x, negative 0.0001. If you plug that in, you get negative 10,000. So the way we would describe that is this sentence. This says as x approaches 0 from the negative side, okay, from the left. So starting in the negatives and heading towards 0. Whenever you head towards a value, if all of a sudden it curves up to infinity or down to negative infinity, that tells you you have a vertical asymptote. You could also have a vertical asymptote where both sides do the same thing, like this. In that case, you don't have one side going to negative infinity. As you approach 0 from both sides, it's positive infinity for the y. But ours doesn't look like that, the 1 over x. So if you look at this value, 0 causes you, if you plug in 0 there, it causes you to divide by 0, and that's where you have a vertical asymptote. So let's graph something else. Let's do x squared plus 5x plus 4. And let's divide that by x plus 1, x minus 8. How many values would cause you to divide by 0 in that problem? Yep. 2 values. What would be the 2 values? -1 and +8. So how many vertical asymptotes do you think this one will have? 2. All right. Let's graph it and let's see what happens at -1 and +8. Let's look at that. Well, definitely have a vertical asymptote at +8. Okay, I can see that one, right? 1, 2, 3, 4, 5, 6, 7. I don't know why it's, oh, I don't think my tick marks are going by 1s. That's why. Let's make the tick mark go by 1s, then it'll look better. Okay, so let's take that again, put that there. And let's draw in a line at 8. So you got 1, 2, 3, 4, 5, 6, 7, 8. We'd have to zoom up a little higher and a little lower to see it getting closer. But this is going to keep going like that, and that's going to keep going like that. So you definitely have a vertical asymptote at 8. What happened to the one at -1? Yeah? It's a hole. Yep. There's a hole in the graph right there. That is not a vertical asymptote. You can tell it's a hole a couple ways. If you go to your table and you try -1, well, it definitely tells you it's an error, which means it doesn't exist on the graph. But just because you divide by 0 doesn't mean it's a vertical asymptote. Divided by 0 means it's definitely undefined. But there's 2 kinds of undefined. There's a hole in the graph, and there's a vertical asymptote. It's always one of the 2. The way that you can tell which one it is right here. You have to look for common factors. Okay, so this part, I think I already said. If, as you approach a certain value, you head up to infinity or down to -infinity, that means you have an asymptote. But how can you tell if you don't have a picture to look at? Look at the denominator and see what values would make the denominator 0. If you factor it and you do not have any common factors in the top and in the bottom, you will have vertical asymptotes anywhere the denominator is 0. If you do have a common factor, you will get a hole instead. Okay, so I could easily make this problem into 2 asymptotes by messing up the numerator so it doesn't factor as x plus 1, x plus 4. Now you'll see 2 vertical asymptotes very clearly. There's one at -1, and there's one at +8. Okay, so make sure you always check for the common factors between numerator and denominator. Okay, so let's see if we can find the vertical asymptotes here. Are there any common factors in the numerator and the denominator in example A? What do you think, Lucas? No, there's no common factors here. There's no x minus 2 at the top. Okay. So that means wherever the denominator is 0, that's your asymptote. There's no holes in this graph. What would make the denominator 0? Yep.
-2. Or 2.
2. Yeah, 2. And then how would you write the equation for the asymptote? Yep.
Y equals 2. Oh, x equals 2.
X equals 2. So this one has a vertical asymptote at 2. About example B. Check for common factors between the numerator and denominator. If there are none, then well, you know what to look for. Would be a vertical asymptote here. Or if you don't think there is one, tell me why. Yeah. Yeah, x equals -3. So it's the number that would cause you to divide by 0 as long as you don't have any common factors. This -1 has nothing to do with the vertical asymptote. This shifts the function down 1. We're going to talk about that next. But shifting up and down will never affect a vertical asymptote. Only shifting left and right would. This +3 is what's shifting left and right. So let's talk about the transformations. First of all, to describe transformations, it has to be in this format. Okay? Something like this, that's not as easy to describe transformations. It's not set up the right way. So let me show you the transformations. Each one of those boxes is going to cause a transformation, either a shift or a stretch. Let's start with the inside. What kind of transformations are always on the inside? And in this case, inside means in the bottom of a fraction. Yep.
Left and right?
So your horizontals. Yeah. Yep. You always have your horizontals. Is A the horizontal shift or the horizontal stretch? Yep. Shift. Shifting is always with adding and subtracting. And since it's inside, it's horizontal. Remember, plus, we did this with quadratics. Plus is going to shift left. Negative is going to shift right. Then what is B going to be? It's still inside, but now it's multiplication.
Horizontal stretch.
That's your horizontal stretch. Just like the shift, it is also backwards. If you put in a big number for B, like if you put in a 4x, that's actually going to cause the graph to compress 4 times as much. Or you could say stretch by 1/4. If you put in a fraction for B, small number, like 1/3, 1/3 is small, it actually makes it bigger. It stretches it 3 times as much. Okay, how about C? It's multiplication like B, but it's on the outside. Yeah?
Would that be vertical stretch?
That's your vertical stretch. And that is not backwards. You put a 5 there, it's a vertical stretch by 5. You put a 1/2, it's a vertical stretch by 1/2. And what about D? It's also on the outside, but we're back to adding and subtracting.
Vertical shift.
That's your vertical shift. Positive is up, negative is down. If B is a negative, you could also have a horizontal reflection. If C is negative, you could have a vertical reflection. So that's what each number does, and that's the order you always describe them in when you write them down. Yep.
Wait, so for A, if it's a plus, it goes to the left, and if it's a negative, it goes to the right?
Negative, yeah, negative goes to the right, plus
Okay.
goes to the left. Yep. Those are your directions. Okay, so now let's try to take a problem, and I want to describe the transformations. Notice this isn't set up the right way. You got to have a 1 on the top, something in front. Okay, Okay, that's not right. So I need to take that and divide it up, either synthetic division or long division. I would do synthetic. So we'll put the 5 on the outside. 2 and negative 13 are going to go on the inside, and it's a very quick synthetic division problem. Bring down the 2. 5 times 2 is 10, and negative 13 plus 10, negative 3. So the way you want to write your answer now is the way I showed you when we learned long division. Quotient plus remainder over the original denominator. If you write it like that, it's going to line things up the way you need them. Quotient. Well, in this case, it's not actually going to be plus remainder because my remainder is negative. It's going to be minus my remainder over my original denominator. So that's better. It's closer to the format. But what I would do is put the 3 in front and make the top a 1. So we've got 3 times 1 over x minus 5. And you could multiply that out. 3 times 1 would give you 3. Let me just make sure we know that's in the middle, not in the bottom. And then the plus 2, I'm going to put on the end. Now with synthetic, you've rewritten it so you can see all the transformations. Oh, and that's actually, don't forget your negative. That's a negative 3 because of this right here. Okay, so how many transformations are happening in this one? Yep.
3.
So tell me what you're looking at to figure that out.
The plus 2,
Yep.
the minus 5, and the minus 3.
That's 2, the minus and the 3.
Oh.
Yeah, so the minus is going to cause a reflection and the 3 is a stretch. So we'll write each one separate. So let's do that first. Let's describe the transformations. What's the first thing that you would write down to describe the transformations? Yeah.
Vertical shift by 2.
So that was in box D. So that's the very last one. Okay, so we are going to write vertical shift 2. I'm going to put that as the last one. So shift up 2. So it is right. It's just not the first one we have to describe. Yeah?
Horizontal shift to the right by 5.
Yep, that's the first one. So shift right 5 units. Okay. What's the second one? Yeah.
Horizontal. Vertical stretch by a factor of 3.
Vertical stretch by a factor of 3. Yep. So vertical stretch by factor of 3. And what's the last? Well, the last one we need to fill in because we already did the shift up 2.
Flip over the x-axis.
So you could describe it as flip over the x-axis, or you could say vertical reflection. Either way. And the horizontal asymptote, that always starts out with what letter? Yep, y, and the vertical?
X.
X. So in this case, your horizontal asymptote let this get really, really big, and this entire fraction is going to get very close to 0. Multiplying something close to 0 by -3 is still close to 0. And adding 2 makes it close to 2. So the only number that really affects the horizontal asymptote is that one. That's all you have to look at. And what about my vertical asymptote? What's that going to be about? Yeah? 5. That's what would make the denominator 0. And there's no common factor. So some of that you could tell by looking at the original problem, like the vertical asymptote, but I don't know if you could tell there was a vertical stretch by a factor of 3. There was no 3 in the original problem. All right, it was a 13, but that's not a 3. All right, so it is important to do the long division, or synthetic. All right, so 48A and B, those are going to be a question we look at together tomorrow. So you won't be able to do that one. And let me just take a look at I think everything else that looks fine. Okay, so 8 through 10, that's just a couple graphing ones that you have to find intersects for on the calculator. Those are quick. And then page 222, just odds on 1 through 7 and 11 through 21. And 48 we're going to do together tomorrow.